Okay, so today we're talking about molarity so that we can do stoichiometry with aqueous solutions. So go ahead and write down the notes on the page and then continue the video so I can explain. Okay, so molarity refers to how concentrated a solution is. So when we have a solution like the one you used in the lab making sodium acetate in the last class, you can't weigh it, because if you did, you would be weighing mostly water. Any aqueous solution is most of its mass comes from water. So we have to talk about measuring it in volume. Like in the lab, you measured out 40 milliliters of the solution, of the hydrogen acetate solution. But you also would need to know how much hydrogen acetate per liter was dissolved in that solution to know exactly how much you were actually using and to do any stoichiometry with the hydrogen acetate. So that's why in the lab we made the hydrogen acetate the excess reactant, so it would not be used to predict how much product you would make. And so, and in one of the lab questions I asked you to solve for the number of moles of hydrogen acetate, but you wouldn't be able to figure out the grams, or you could figure out the grams, but it would be a useless number for that particular lab because, most of the mass of that aqueous solution would be from water. So what does molarity mean? It means concentration. So if you imagine making Kool-Aid, and let's say you decided you really like sweet stuff, so you dump in 2 flavor packets and you double the amount of sugar that's in that Kool-Aid. You've just upped the concentration. You've increased the number of dissolved particles in that solution. And it would be darker in color if you put in more flavor, with all of its coloring. And it would be much, much sweeter because you'd have more moles of sugar, even though we don't measure with moles in the kitchen. You would have more moles of sugar, and so it would be more concentrated. Let's say we were talking about our solute, our thing being dissolved, as being sodium chloride. So if I have a beaker, and let's say this is a 1 liter beaker, so 1 liter, and I dump in 1 mole of solid sodium chloride. So I'll just draw like a big chunk of salt. Let's say it's a big block of salt. And I dump this into the water. If that's 1 mole that I'm putting into 1 liter, then I have just made a 1 molar NaCl solution, because molarity, that capital M stands for molarity. It means number of moles per 1 liter of solution. And if I put 1 mole in to a 1 liter container, that would be a 1 molar concentration of sodium chloride. If I doubled it but kept the volume the same, then all of a sudden my number of moles is 2, my number of liters is 1. Well, if I have 2 moles in 1 liter, then now I've got a 2 molar solution. If I cut my volume in half and just went with 1 mole, but I only had a 0.5 liter container, or 0.5 liters of water, then that would still be a 2 molar solution, because 1 divided by 0.5 is 2. If we take a small sample, if we pour some of this 1 molar solution into a 50 milliliter beaker, it's still 1 molar NaCl, because we're not changing the concentration. If I have a certain concentration in this beaker, meaning a certain number of dissolved particles per liter, then if I take the volume way down, there's still the same number of particles per unit volume. So let's take a look at a question that we might have to answer. How many moles of zinc chloride are there in 2.5 liters of 1 molar zinc chloride? We're going to do this as dimensional analysis, and I'm going to start with 2.5 liters of NaCl. Now, you might be questioning, why would you start with the liters? You were given two numbers. 2.5 liters, 1.5 molar. 1.5 molar is a relationship between moles and liters. So if I write this off to the side here, this is saying there is 1 mole of ZnCl2, 1.5 moles 1.5 moles of ZnCl2 per 1 liter. So whenever we have a relationship between two different units, that's usually not going to be our starting point. Notice that this is a simple measurement. It only has one unit. So what I'm saying is molarity will never be your starting point. Molarity will always be a step along the way to convert between moles and liters. Okay? So let me get that out of the way so I can finish my problem. So now I'm going to go from the unit that I have, liters of NaCl, and I'm going to go to moles. All right. Now, do you remember? You can always rewind and watch it again. What values do you think we're going to put next to moles and liters? Okay. So 1 liter in this case contains 1.5 moles. That's what 1.5 molar means. Molar means moles per liter, so 1.5 moles in 1 liter. For this step between moles and liters, you will always put a 1 in front of liters, and the molarity goes in front of moles. All right, so we should get about 3.75, or rounded to 2 sig figs, 3.8 moles of NaCl. All right, let's try another problem. How many liters of 0.800 molar HCl are needed to react with 32.5 grams of zinc? So we need a balanced equation for this one. HCl plus zinc would be single replacement. So we get ZnCl2, because zinc is plus 2, and then H2. We need to balance with a 2 in front of HCl. Excuse me, in front of HCl. Again, what number is our starting number going to be this time? Okay, good. We don't start with molarity. We always start with a number that has a simple unit that is not a conversion between two different units. Molarity is a conversion factor between moles and liters. We're going to start with 32.5 grams of zinc. Okay, we're going to convert that using the molar mass of zinc. We're going to go from grams of zinc to moles. 1 mole is 65.38 grams from the periodic table. And then we have to go from moles of zinc to moles of HCl. And from the balanced equation, that is a 2-to-1 ratio. All right. At this point, we haven't done anything different than the previous stoichiometry problems we've done over the last 2 weeks. It's grams of A to moles of A to moles of B. The difference is, in the past, we would have gone to grams of B, grams of HCl, but since HCl is an aqueous solution with a molarity, we're not going to go to moles. We're going to go to what? What do you think is the unit on top? The unit on bottom will be moles of HCl. The unit on top will be liters of HCl. And as we said in the previous question, a 1 always goes next to liters, and the molarity, in this case 0.800, goes next to moles. And so then the last step is just taking liters to milliliters. And 1 liter equals 1,000 milliliters. That's a conversion factor you should remember, hopefully. I do the math, I should get 1,240 milliliters of HCl. All right, last question. This one's going back to the lab. We used 40 milliliters of 0.95 molar acetic acid or hydrogen acetate in the lab. with 2 grams of sodium carbonate, or sodium hydrogen carbonate. How many, but we knew it was the excess. So that means we must have needed less than 40 milliliters if it was the excess, because we had some vinegar or some hydrogen acetate left after the reaction was over and the bubbling stopped. So let's see what we should have needed. So we have to write our balanced equation. So NaHCO3 plus C2H3O2, and that yields NaC2H3O2 and H2CO3. Now I will tell you something about the H2CO3 that I didn't bother with telling you in the lab. That actually then breaks down into water and carbon dioxide, which is why you saw bubbles. And then what was left in the beaker, in addition to the excess hydrogen acetate, you had that water that then had to be boiled off. But either way, the balanced equation is still this. Everything's in a 1-to-1 ratio. So we're going to start with, well, what do you think? What number are we going to start with? Okay, 2 grams of our limiting reactant, NaHCO3. We're going to convert that to moles, right? And so we're still at moles of A. And 1 mole, let's see, get out the calculator. Okay, so the calculator tells me that's 84 grams, almost exactly. Oops, I forgot my label there. And then for moles of A, moles of NaHCO3, we're going to go to moles of B, which in this case, we're interested in the hydrogen acetate. And that was 1-to-1 from the balanced equation. All right, now we're going to go from moles C2H3O2 to liters of it. And this is where my molarity comes in. 1 liter is 0.95 moles. Oops, there we go. Oops, and then we're not ready for the equal sign just yet. We have one more step because we have to go to milliliters. So milliliters of HC2H3O2 over liters. 1 liter is 1,000 milliliters. And let's see what this gives us. Let's get out the calculator. Okay, so to 2 sig figs, which is what my molarity has, 90.95, that's 2 sig figs, I get 25 milliliters. So we used about 15 extra milliliters, which is why this was our excess reactant. We had to boil it off, and your boiling beaker smelled like vinegar. So there you go. Make sure you come to class with any questions that you might have over molarity, and we'll work more with this next time.